Hello, and welcome to this talk on multi-cluster object storage, the future. I'm Abhishek Lakshmanan. I'm a senior software developer at SUSE. First, we look at the agenda. We look into the basics of object storage and SUSE Enterprise Storage, and then we cover about Ceph. And then we go into the multi-cluster part of object storage. We look into the motivation, the past architecture, the current and the future designs. First, we get into the storage basics. So, storage is basically three categories. You have block storage, you have object storage, and then you have file system. So first we look into block storage. So this is the most traditional form of storage. So data is always written in fixed size blocks, and this is the one that is most common with everyone, that everyone is aware of. It is very fast, and then you have protocols like SATA, which is your hard disk protocol, iSCSI, then fiber channel over Ethernet, etc. And basically you have disks which actually always write in blocks, and that's how this concept of block storage came about. And that's like the most popular form of storage. It only stores data, and then there's no metadata as such associated with it. Next, file system. So file system is like the more traditional form that we are all acquainted with. So it's a layer over the block storage usually. So you have files, and then you have meta things called directories, and you have users, ACLs, and then attributes on files like modified time and many other custom attributes that you can attach as key value pairs. The files are generally mutable, and then you always have sharing semantics. So you can share it to a different user or a group. And the common protocols, like when it comes to local file systems, you always have file systems like XFS, ButterFS, NFS, and then you have network file system like the network file system, NFS, and Zamba. When it comes to object storage, so it's not a traditional form of storage, so it is like in the modern era cloud form of storage, so it's usually REST based. You have the concept of like users, accounts, and then containers or buckets or something like that, which kind of derive the concept of a folder. And then these are always like in a flat namespace within a container. So you can, create a pseudo folder like structure, like naming your files with a directory like structure, but otherwise it's just generally under a container you just have a flat namespace of objects. You do have sharing semantics because you have users and accounts, so you can technically share a file with a specific account. And then since it's cloud based, then your backend system can do many things on a life cycling sort of a thing. So you can transition objects into a colder tier of storage, or you can delete them after a certain number of days or something like this. And since data as such is present, in the backend in form of small objects, you can actually create really large files. So for example, a movie of 2 terabytes would be actually many 2004 megabyte files. And the commonest object storage protocols are AWS, OpenStack, Swift, Azure, and Google Cloud. Next we cover about Ceph. So Ceph is this unified storage system that's deemed to be the future of storage. So it provides all the three forms of storage. So you have object storage, block storage, and file system. So at the lowermost layer, there's something called RADOS, which is like a reliable, distributed, autonomous object store. And this takes care of replicating or erasure coding your data, and then placing your data according to your failure domains, so that you can always make sure that the data is always safe. And this RADOS is presented as an API called librados, which the other protocols build on top of. So you have the object storage, which uses a librados to directly store files as objects. And then you have block storage, which essentially uses the librados API to actually store blocks as objects. So even though the disk is presented to you, it's actually underneath just a connection of objects. And then you have file system also, which is actually stored as objects underneath, and the metadata, which is actually stored as metadata on objects. So when you talk about the architecture of Ceph, you have like two kinds of daemons. You have monitors, and then you have object storage daemons. The object storage daemons are essentially your plain old disks which have a daemon running on them which intelligently plays data. And then monitors take care of cluster membership and then making sure that everyone in the cluster is alive and making sure that the placement is going on according to the plan. So the clients actually always talk directly to the OSDs after getting cluster information from monitors. So there is no other middleman involved. So it's always like clients directly write to the disk themselves. So that avoids any sort of middle layers in between. And that kind of gives a lot of flexibility on terms of storage. And the lowermost API is this thing called RADOS. So it's short form for Reliable Autonomous Distributed Object Store. And so you have object placement based on algorithm called Crush, which essentially calculates hashes. So this allows for sort of infrastructure-aware placement strategies. So you can make sure that the data is like placed into a domain that always fails when the other domains do not. So for example, you can always make sure that the data is placed in different rooms or different racks, so that if the power goes down on one rack, you can make sure that the 2 copies of the data is still alive. And the semantics always provide for strong CP model of consistency if you're looking into the cap theorem sort of a thing. So it's always consistency and over partition tolerance rather than availability. So which makes sure that like if you have a net split and then both the partitions are down, then you cannot actually write. But whenever you write, it's always ensured that the consistency is always correct. And the clients always talk directly to the storage nodes. And you have this concept of pools, which are broadly like a meta classification of data. And then objects pretty much stay in a flat namespace within pools. And the protocols like RADOS, block devices, file systems, and RADOS gateways actually built on top of this flat namespace. Moving on to the next section. In this section, we are going to cover about RADOS gateway, and we are going to peel the RGW onion and see what layers are involved, particularly in the context of multi-site, about what layers that needs to be addressed. So when we talk about RADOS gateway, it's a RESTful client to the Ceph cluster. So it's basically a client that actually converts HTTP requests into librados requests, and it supports the popular S3 and the Swift OpenStack APIs. It scales very well horizontally because it is stateless, so you can put multiple RADOS gateways behind a load balancer, and that way you can scale according to the requirements of the site, putting multiple RGWs behind and not becoming a single point of failure. And you can also host them in very thin nodes that only host RADOS gateways. When we talk about the data itself, the data layout in RGW, so it's broadly 2 categories. So you would have the metadata, that is essentially the users and the accounts. So when you broadly look at the S3 API, there are like 2 categories. So you would actually have a creation or a deletion of a bucket, and then you would actually store the data in objects. So the bucket itself is the metadata, and then the objects contain all the data that is relevant. And of course, there are like multiple APIs that would like store my objects in multiple parts or something like that. That's more of an implementation detail, but broadly about data itself, it was just objects that is considered as data. And then metadata is stored in separate pools compared to the data pools. So that allows you to create different categories of storage. So you can have SSDs for index pools, that's very fast, and you can store data in like hard disk and do erasure coding on them. Data pools can only be replicated, and data pools can be either EC or replicated. We also support multiple placement pools, so similar to the Amazon XAMZ storage class, so you can actually have multiple classes of storage and transition between them. So this allows you to actually design 2 different tiers of storage. So you'll have one slow tier that's hard disk only, and then you can have a faster tier that's SSDs and replication or something like this, depending on your site requirements. And looking at a schematic of how this data itself is placed. So here's a schematic. So here you have 2 different data pools. So one is a SlowX 8+3 EC pool on hard disk, and then you have a 3x replicated SSD pool, for example. And then you would have metadata. So you would have the meta pool that is containing the users and bucket info. So how we do it underneath is we actually have this concept of namespaces and RADOS for pools. and so users fall in one namespace and then bucket info falls in another namespace. And then you have a pool that actually stores the index of objects in a bucket. So that's called the bucket index pool. And it's generally recommended that you use a SSD for this because index operations can be faster that way. And now we cover why we need to do multi-site. So when we talk about the motivation for doing a geographically redundant storage, the first thing that comes to mind is always end user latency. So if you have customers situated in Australia, for example, and then you're located in Prague, then the speed of light alone makes it like a 300 millisecond delay before you can actually reach to your customer. And given that that would actually translate to a seconds of delay that humans can actually perceive, you would always want to locate close to your customers. And the other thing is disaster recovery. So the whole data centers can fail, or power can fail, or natural disaster can strike. And over this, you also have compliance requirements that say that your data must be stored in multiple data centers that's not geographically close to each other. And depending on very critical data, you might actually want that geo-redundancy. And when we talk about geo-redundancy in the context of Ceph, you have Ceph is always doing synchronous writes, and synchronous writes is great if you actually have data centers that's really close by, so where the latency doesn't matter. Otherwise, for a geographically apart cluster, synchronous write is going to be very costly and you cannot actually pull it off. Redux does this strong CP consistency, so it only does strongly consistent writes, so you cannot actually get away with that. And that high latency would be bad enough for most applications. So in the context of object storage itself, eventual consistency will be okay for the most part of the applications. And RGW does its own mechanism instead of replicating from at the Redux level, just because the transaction semantics that we would require for this sort of a scenario would be better handled at the upper layer. This is just because, like, when you're talking about Redux, it knows nothing about the metadata. So as far as user itself is concerned, he would prefer the bucket and then the bucket index to be consistent with respect to the objects actually stored in the bucket index. And this sort of a scenario is not exactly something that Redux is aware of, so you might actually have tails of the objects being synced to the other side, but the other side has no idea that this is actually a part of an object that has not been created yet, or something like this. So we always want the replication to be handled at the upper layer, and that's why RGW has its own mechanism for replication. And when we talk about multi-site itself, it's been supported ever since Luminous release of Ceph, so ever since SAS 3. And these are like the broad terminologies that we should know of, like, before we delve into the details. So at the lowermost layer, you have something called as a zone. So zone is essentially a group of multiple RGWs, for example, and it's usually a single Ceph cluster. You can actually even have multiple zones in a Ceph cluster should your compliance requirements require that, but most commonest use case is that you would have one zone for a Ceph cluster, and then you would have a collection of zones called a zone group. And over this, you have something called realms, which are essentially namespaces. So when we talk about replication itself, data is replicated across zones within a zone group always. Metadata is replicated across zone groups, and nothing ever leaves a realm. So realm is like the top level namespace container sort of a thing. So you can actually have multiple realms to partition data. For example, you have internal data and customer data, and then you don't want any sort of sharing between these. Then realms would be the ideal thing to namespace these sort of things so that nothing ever gets shared between them. And over that, you have something called as a period, which is like the current configuration structure, which essentially is a snapshot of the whole thing. So when we talk about the current architecture, we currently support active-active multi-site. So which means that data can be actively written in both master and non-master RGWs. So local operations are synchronous to the local Ceph cluster that you're contacting to, and then remote operations would be asynchronous. So what happens is that any sort of metadata operations will always be forwarded to the master zone of the master zone group. So the whole concept is designed across the thing that data is always constantly changing, whereas metadata changes are not so constant. And whenever metadata changes happen, these obviously have a system-wide effect. So for example, when it comes to something like creation of a user itself, you would want every site to be actually known about this concept of this user being created. And also similarly, when a bucket is being created, you want the bucket namespace to be reserved across all the other Ceph clusters, all the other clusters as well. And that's how the current architecture is designed across. And the current architecture already supports dynamic reconfigurations without the need of restart of RGWs. So this allows for failover of a master zone to another secondary zone without the need for needing to restart the whole system itself. And here's a schematic that shows the current scenario. So we are talking about one realm gold, which looks like this. So you have one zone called US East, which is like the master zone, and then you have a secondary zone called US West. So data is actually replicated across both US East and US West, but US East is the master when it comes to metadata operations. And you have another zone group called EU. So no data is shared between US and EU, but metadata is shared, so you would have the same users and the bucket namespace in the US and EU are following the same. And in the EU, you would have a different sort of a master, which would be the source of truth as far as EU's bucket creations is concerned. And you can have another zone called silver, another realm called silver that would actually have a whole different schematic, and that's completely supported. So when you talk about the sync process itself, how it looks like is the metadata changes are always handled by the metadata master. So when you look at the previous scenario, US East would be the source of all metadata master changes, and any sort of metadata changes involves at least one trip to the master. And similar to the concept of AWS, like you would have bucket creation is supposed to take a bit of time because it has to be relayed across all the AWS regions. And that's the same concept here, that a bucket creation would actually be forwarded to the metadata master, and only when the metadata confirms the creation is when the bucket is created in the local site. Data changes can be always processed locally by the local zone that you're contacting to, and it's forwarded to the remote zone, which would actually sync the changes then. This whole concept of sync itself allowed for designing of something called as sync modules. So since the data creation itself is async, so you can actually have zones that act on basis of this asynchronous information and then actually forward it to external systems or something like this. And they can decide what to do with this sort of data. So this allows for example, once you know that the data is available on the remote site, you can just forward the data to something like a ElasticSearch, which would allow you to, for example, dissect the metadata and do interesting analysis on the metadata, like saying like you can analyze, like query like how many meta users were created in this period of time, or what's your commonest load period or something like this. And you even have support for something called cloud sync, so you can actually sync to an external cloud system, including AWS itself. And you can have a zone that would actually archive every copy of the data that's ever been created, that would support no deletions, which can do its own compliance sort of scenarios. Now we look into the limitations of the current system so that we can see why we need to design a new system. So the current multi-site features actually target the cluster administrator. So you have a site-wide replication, site-wide failover, and cloud sync policies or any other sort of sync modules which act at the entire site. So what this means is that you can actually replicate a whole data center to another data center, or fail over a data center to make another data center the primary data center, but you cannot configure this at an individual level. So the whole flexibility is at the entire site level, and given that more applications actually know like what data is critical and what is not, and many of these do not translate to a site-wide setting, we need to rethink. So ideally, like tiering and placement and replication strategies, many of them should be targeting the bucket owner as well, since the bucket owner would be the one who would be like really aware whether the bucket is actually critical for being replicated twice, or whether it is a not so important bucket so that it only needs lower redundancy storage or something like this. and also like the different classes of storage that you would use a bucket in, whether it's a fast storage or whether it's a really slow archived data that's only accessed very infrequently. And many of these decisions are actually best made by the bucket owner rather than the site administrator, because many of these cannot be just done by a blanket site policy. So the goal ultimately would be to have the bucket owner control these aspects. So the goal would be that the bucket owner would be able to configure the replication at a bucket level, and he should also be able to migrate buckets between different zones, or fail over a bucket on his own. And the idea also eventually would be to actually sync individual buckets to or from cloud, so that you can actually decide that this bucket is actually worthy of archiving in a public cloud as well, or this public cloud use case for this bucket. So this should be actually stored in the public cloud. And the advantage is that then you would actually have a site-wide policy set by the administrator, the site admin, like the current scenario, as well as the bucket owner actually deciding on the more fine-grained details on how critical the bucket data is, or what sort of replication policies to apply, and something like this. Moving on to the next section, so we are going to look into the future design and what we have in store for the future. So firstly, the motivation, like the most common thing is that the clusters scale out. You would always have more data to be stored, and you would want to store it in different locations. So cluster scaling out is a natural thing in these data era. The other thing is like organizations also scale globally, and then you also have redundancy requirements in organizations that would be across cloud providers, across geographies. So as an organization itself would have multiple cloud strategies where they would actually back up to Amazon cloud, or they would back up to Azure cloud, as well as their own data centers in different locations. And as an end user developer, you also want API consistency. So you don't want to write for 4 different cloud providers, and you don't want to actually write an application that would suit for your data center, and write a different application for your customer, and then using a different protocol for Azure and something like this. What you would want is like to stick to a single API, and in that respect, the S3 API is kind of a standard object storage API across many cloud providers. So you would preferably want to write an application in a single object API, and S3 API is great for that. And the other thing is like in the modern edge computing sort of a scenario, where you would actually have applications breaking into cloud, or like breaking into the data center, exporting data to the cloud, or importing data from the public cloud into your data center. And these are the sort of modern use cases that we also want to support. Reviewing back on what the typical RGW onion looks like, this is the typical librados backed Rados gateway. So you would actually have users plus bucket info pool. You have like 2 different layers of metadata, and finally the data. So at the top level, metadata is just the user and the bucket. Metadata about the bucket itself, like who owns the bucket and what ACLs it has. And the lower layer, the one is like you have a metadata about the index of the objects stored in the bucket. So that's the bucket index pool. And then finally you have the data pool, which you can have multiple data pools, which are like replicated or erasure coded, or having different redundancy requirements. So ultimately you will have the object in the data pool, and then you have all the meta information associated with the buckets at the upper layers. And let's look into some common use cases in a scenario where you would want to break out. So one common use case is like a protocol translation, where you would actually want to host your bucket in a public cloud, but you would want to access it in band via Rados gateway. So your Rados gateway is the source of all truth. So you would actually use RGW to actually host a bucket in AWS cloud, for example. So you would actually want a bucket called foo in Rados gateway namespace, but that would actually map in the backend to a namespace in the public cloud, for example, a bucket bar that your organization owns. And the SC access itself is done by the SC credentials configured in RGW. And RGW also stores its own ACLs as attributes in the S3 object. And you can also optionally configure other things like lifecycle and encryption on top of this. So the thing would be that RGW would be accessing and mediating the metadata. So your organization controls like how the end user actually uses it, and it's only via the RGW. But the data actually is also landing in a public cloud. Also, another aspect to note is like if you want to actually run Ceph in a public cloud, it would be more expensive than just using S3 service of a public cloud to just use a storage. So in that sort of a scenario, you can actually break out to a public cloud where you're using the public cloud's S3 API, but you would be actually mediating access via RGW. Another same aspect is like you would have a more hybrid use case where the data in the public cloud is also something that you would want to access from the public cloud itself. So you would actually initially store the bucket data from RGW, or you can actually feed it in via the S3 API itself. So you would actually map bucket bar in AWS S3 to a bucket foo in RGW, and you can access it in both ways, like where both RGW can access it as well as you can access it from your application in the public cloud. So this sort of an out-of-band mode is like a more complex use case, but it's something that modern applications can very well use. Another common scenario is this edge computing sort of a use case where you would have a bucket in RGW namespace, and then you would have two layers. Like one would be like you would be actually backing up the object in your standard data center in Ceph storage, so using Rados, and then it will also have a pass-through mode where you would actually just directly store it to the S3 cloud instead. So reads can actually try like initially trying to hit the local Ceph cluster, and if it's failing, it can go and try and fetching it from the public cloud. And you can also have different sorts of write back modes or a write through mode. So you would actually either write through directly to the public cloud, or you would have a write back mode where you would actually use the S3 cloud, the Ceph cloud locally as a local caching layer, and then you would actually have a background process that would migrate this data back to the public cloud. So this is like a very modern sort of a scenario where you'd have a container spinning up and then storing data locally in your local data center, but eventually you would want the data to be moved out in the public cloud. And there are more like hybrid use cases where this sort of scenario is like ideal. And challenges for making this happen. Like we want to make the bucket layer abstraction sufficiently general and flexible. So you would want to have local storage in Rados as well as pass through to an external remote provider. And the other more complex aspect is like credential translation, that you would actually want to map a user credentials down to an S3 credential. So you would want this also to be configured at a site level or a organization level or a bucket level. And also the other thing what we want to configure is like the current multi-site is always happening with synchronous metadata and asynchronous data replication, and you would want more fine-grained control where you would want synchronous replication as well for certain workloads. So that's sort of a change from the current scenario. And the other thing would be like streamlining and getting data from the public cloud back into the Ceph storage. So that would be like you would actually want something like an AWS Lambda service that would identify a service onto a bucket, right, and notifying the RGW, and then that RGW can go download this object into the local store, and also making the setup of this sort of a complex scenario more easier since it's already pretty complex. So looking into the roadmap of what we have in future, so the first things we need for this to happen is like the bucket granularity sync. So you would want individual buckets to be able to decide on their sync policy rather than the entire site-wide policy that we have currently. So the current scenarios only allow for a site-wide sync with disabling of specific buckets, but we would want to have sync to happen at the bucket level so that the buckets can individually decide. So the bucket owner can individually decide whether a bucket should sync or not. And you would also want future work to allow to sync to and from different cloud providers. Another work that is in progress is this project called Zipper, where you're having internal layering abstractions like VFS model, where you'd sufficiently want the RGW layers to be abstract enough that you could actually backend write not only to a Rados store but to, for example, a local database backend like SQLite, and eventually you would be able to leverage this system to write to a public cloud or any sort of cloud provider. So looking into what we have currently in Octopus. So first what we have is like sync policy. So this is like a broad policy at a zone or a bucket level, So you would have initially sync policy at the zone level that controls the site-wide replication, and you also have this at a bucket level, and these can be created in multiple groups, so which makes it easier to apply policies in groups. And you have something called as a sync flow graph, which essentially is a graph that decides the direction of flow of sync. So you can have bidirectional sync or a unidirectional sync. So for a backup sort of a scenario, you would want a unidirectional sync. And what is also supported is a sync pipe sort of scenario, where you would have a zone that's only piping layer, which would essentially just hold the data temporarily and then upload it back to another zone. And using these primitives alone in Octopus, you have a lot of use cases that can be done. So let's look at some common use cases that we can do with the current experimental features. So one is like a full backup zone, which is already currently supported, but also you have more fine-grained control. So you can actually have a unidirectional sync that says that you're only syncing in one direction. So you will not have the data being written to the remote site, but only written at the local site and then backed up to the remote site. And you can be more creative and then only apply sync on a filter the sync based on certain object name patterns or a bucket name pattern, and do this on certain tags on the objects. For example, you would say that objects with tag saying backup equals true are the only objects that you need to be backed up to this cloud, to the remote site. And then the more useful scenario would be like you would have a specific bucket that would be mirrored to a remote site instead of the whole site. So you would have a specific bucket that is like very important that you would want to back up to three different sites. And you can also control the write direction, saying that site A and B can actually write and read from the bucket, whereas site C is a pure backup site, so it can only archive every bucket. And another thing that's very interesting is like storage class translation. So you would actually have a tree replica copy in your primary data center, but in a remote site it will be a lower redundancy, or it will be an erasure coded pool. And similarly, you can have buckets that lifecycle in a similar way, saying like you would say that this bucket is actually 3 replica here, but in the remote sites it will be in the 2 replica sort of a zone. And this already allows for very interesting use cases. And this concludes my presentation pretty much. Ideally, this would be the area where I would be opening the talk for questions. So in this digital format of the SUSECON, I would ask you to post your questions in the SUSECON Digital website, and I'll try to answer them. Thank you.